So when we speak of liquid-liquid extraction or extraction, we simply mean two phases being contacted and two phases being the product of this contact of the two phases. So we separate components of a given mixture with the use of a solvent. So it is needed and it's a requirement that the two phases that has to be contacted should be chemically different. So the transfer of components from one phase to the other is driven by what we call deviation from thermodynamic equilibrium. Now, separation is according to the difference in physical and chemical properties, such as differences in polarity and the hydrophobic or hydrophilic character of the solvent. Now, mentioned here in the first bullet that you have contacted two phases so that the components of the feed can be separated from each other. The product will also be resulting to two phases. One is called the extract. The extract contains the component of interest extracted from the feed, and the other one is the raffinate. Now, the solvent-rich phase is what we call as the extract. The water-rich phase is what we call as the raffinate. So these were the phrases that are used to refer to these two product phases coming from the contact of the feed and the solvent. Now, some application of liquid-liquid extraction is in the removal of contaminants from a given mixture or the recovery of a desired component from also a process mixture. So a specific example that's stated here is the removal of acetic acid from water, which we can also accomplish through the process of distillation. Now, if we use liquid-liquid extraction, the solvent has to be organic. Now, in the case of the removal of the high molecular weight fatty acids from processed vegetable oil, we also use an organic solvent. In this case, it's specified to be propane. Now, the two alternative processes here are distillation, but the second one is high vacuum distillation, which will be highly energy extensive in terms of use. So that is why some would rather resort to the use of liquid-liquid extraction, of course, with an option at the end to recover the solvent for reuse. Now, another one here is in the recovery of penicillin from fermentation mixtures. In the case of metal processing in mining, so we can separate valuable metals, specifically metals, from their mixture using liquid-liquid extraction. Now, there are two main cases of, or classes rather, of solvent extraction equipment. One is the very simple mechanically agitated mixer with a corresponding settler. And another one is the one we accomplish through the use of columns, wherein mixing is done by the flow of the fluids themselves. So in the case of the mixer settler, you can read on this in Jan Kuplis, and even I think in your handbook, you have this also. You have a mixer that homogenizes the mixture, then later on, the phases, the product phases are separated. So what's separated on top of the mixture is the extract, the one at the bottom is the raffinate. Now, in the case of vessels in which countercurrent extraction is carried out, mixing is done by the flow of fluids themselves. Now, when we speak of the feed, it's the solution that contains the components to be separated, or the component we are interested in, and it's composed of the feed solvent we call the carrier solvent and the solute. So the component that we're interested in is the solute. We know that it's the solute is because in terms of composition, it's the one that is present in the least amount. So of course the solvent, having it solving the solute, will be in terms of amount be a lot more than the solute. Now, there are terms that are very important in your understanding of extraction, and these terms you can also read at the beginning part of this section in your handbook. So the extraction solvent, or we refer to as the separating agent, the one that accomplishes the actual separation of the component from the feed. So this is the immiscible or partially miscible liquid added to the process to create a second liquid phase for the purpose of extracting the solute or the solutes from the feed. Now, this extraction solvent or separating agent is comprised of the extractant dissolved in the liquid diluent. So your liquid, the carrier liquid is the diluent, and the extractant, the component that really accomplishes the extraction, is dissolved in this diluent. Now, at times, a modifier may be added to the diluent to increase the solubility of the extractant or otherwise enhance the effectivity of the extractant. So that's the modifier. Now, we also have here the concept of the theoretical or equilibrium stage. So, in the separation processes that we have discussed, one is gas absorption in HMT then. Then, now we have discussed distillation just last week. So, all of which have the concept of the theoretical or equilibrium stage applied to them. So, in here, we will also be using this particular concept, and this is used here to refer to a device or a combination of devices that accomplishes the effect of intimately mixing two liquid phases until equilibrium concentrations are reached, then physically separating the two phases into clear layers. So we will be forming layers here, the extract and the raffinate layers, or the two product phases that is. In here, when we speak of the extractant factor, this is referring to the ratio of the slope of the equilibrium line with the slope of the operating line. If these slope values are not given or impossible to give, especially if we don't have an equilibrium line, then the extraction factor is also equal to the ratio of the flow rate of the feed to the flow rate of the solvent. And most of the time, this is the one that is being used. Extraction ratio being equal to the flow rate of the feed over the flow rate of the solvent. When we speak of separation factor, this one is analogous to the use of the concept of volatility in distillation. So if we have volatility in distillation as relative volatility, then in here in extraction, its equivalent is the separation factor. Now, the distribution coefficient, which later on at the latter part of this topic we'll be using in problem solving, referred to also as the partition ratio or the distribution constant, is the solute concentration in the extract phase divided by the solute concentration in the raffinate phase at a condition we call equilibrium, or after equilibrium is already attained. So it's not just the any ratio of the solute concentration in the raffinate to solute concentration in the or rather, so it's not just the ratio of the solute concentration in the extract to solute concentration in the raffinate, but it has to be the ratio of these two concentrations at equilibrium. And that would be the distribution constant, the distribution coefficient, also known as the partition ratio. Now, for dilute systems with straight equilibrium lines, the partition ratio is equal to the slope of this equilibrium line. So that's your partition ratio. Now, the loading capacity. So when we speak of the loading capacity, this is the maximum concentration of solute the extract phase can hold before two liquid phases can no longer coexist or solute precipitates as a separate phase. So the maximum concentration of solute in the extract phase before, shall we say, before solidification of the solute starts to happen, or when your solutes start to crystallize out of your extract phase. So that particular maximum amount is the loading capacity or maximum concentration of solute before crystallization or solidification of the solute happens in your extract phase. Now, the partition ratio that we discussed here in the previous slide, this one is given or represented by this formula. So, partition ratio is the concentration of the solute in the extract, concentration of the solute in the raffinate. So, you will know later that Y is concentration in the extract and X is the concentration in the raffinate. So I is any component that we like to refer to. So that's the partition ratio, also known as the distribution coefficient. So high partition ratios generally allow for low solvent use, smaller and less costly extraction equipment utilization, and lower cost for solvent recovery and recycle. So the higher the value of this, the more economical is your processing, your extraction process, that is. Partition ratio of the order of 10 or even higher is desired for an economical process. So this value is taken from Paris. Excuse me. So in terms of solute selectivity, I think the term already implies what does it mean. So it is important not only to recover a desired solute from the feed, but also to separate it from other solutes present in the feed and thereby achieve a degree of solute purification. The selectivity of a given solvent for, let's say, solute I compared to solute J is characterized by the separation factor alpha sub ij. How selective is your particular solvent to extract specifically component I compared to component J in your feed mixture? That is represented by the separation factor. And in here, you could see that it's actually the ratio of the two distribution coefficients or partition ratios of the components, that I and J. How selective is your solvent to take out I or separate I from J in your feed mixture. Now here, just like relative volatility in distillation, values must be greater than 1 to achieve an increase in solute purity on a solvent-free basis. So meaning the higher the value of alpha is from 1, or if it's equal to 1, it's easier to separate your solute, your given solute, from the other components later on that might go with it after it has been extracted by your solvent. Now, when we speak of mutual solubility, so low liquid-liquid mutual solubility between feed and solvent phases is desirable because it reduces the separation requirements for removing solvents from the extract and raffinate layer. So it has to do also, this one has something to do with solute selectivity. We don't want that our solvent will also has a certain degree of affinity to the other components in the feed. We want it only to be selective of that particular solute that you want to separate from the feed. That way later on, you will not have any problem of having to reprocess your extract phase and separate the other components that your solvent may have also taken away from the feed that is not part of your solute, or that is not your solute I. If it's solute I that you really prefer to be separating from the feed. Stability, of course, it has something to do with your solvent being stable. So it has to have little tendency to react with product solute. No reactions here because we're talking about only unit operations. So we don't want to burden ourselves with reactions. And in the process also eliminate the formation of unwanted byproducts, causing a loss in yield. Now, also, it should not react with feed components or degrade to undesirable contaminants that cause development of undesirable odors or color over time, or cause difficulty achieving desired product purity, or accumulate in the process because they are difficult to purge or separate. Now, the solvent has to have low viscosity. This is a given. So low viscosity is preferred since high viscosity generally increases mass transfer resistance. We know this. The more viscous a solution, the greater is the mass transfer resistance. And liquid-liquid phase separation will be difficult if viscosity is high. An extraction process can be operated at elevated temperature to address the problem of a very viscous feed solution. Which this time it could lower the viscosity of your feed. That way, your mass transfer performance or the mass transfer is more effective. in that case. So we need to elevate the temperature or simply increase the temperature to lower down viscosity. Now, recoverability. This has something to do with cost. The solvent also costs money, so it has to be recovered and reused. As much as possible, it could be reused in subsequent extraction processes. Now, density difference has something to do with viscosity, the solvent property in the previous slide. So here, a difference in density between solvent and feed phases on the order of zero point 0.1 to zero point 0.3 is preferred. So the difference in the density of the feed and that of the solvent should be on the range of zero point 0.1 to zero point 0.3. A value that is too low, that is lower than zero point 0.1, makes for poor or low liquid-liquid phase separation and may require the use of a centrifuge. A value that is too high makes it difficult to build high dispersed droplets population density for good mass transfer. That is, it's difficult to mix the two phases together. That means the feed and the solvent phases, and maintain high hold up of the dispersed phase within the extractor. But this depends on the viscosity of the continuous phase. What is this continuous phase? This is actually your feed phase. So we will learn that later. Actually, it depends on the process. The continuous phase could be the feed or it could be the solvent, depending on what the problem specifies. But when we speak of the continuous phase and the dispersed phase and extraction, it could be the feed or the solvent. So continuous could be feed. Of course, the other one will be dispersed. That's the solvent. Some problem says that your feed should be dispersed to your solvent, which is the continuous phase. So it's the problem that dictates which of the two is continuous or dispersed. This has something to do with flooding again. So we had flooding considered in the design of the, if you recall, the gas absorption tower. We will also consider flooding in the design of our extraction tower here. Okay. Now, safety. So solvents with low potential for fire and reactive chemistry hazards are preferred. So this is a given. And interfacial tension. So there is a requirement for density. There is a requirement for viscosity, but it's not really that specific in terms of actual values. There is also a requirement for interfacial tension. So preferred values for interfacial tension for your solvent between the feed and your solvent phase specifically generally should be in the range of 5 to 25 dyne per centimeter, or that's 1 dyne per centimeter being equivalent to 0.001 Newton per meter. Now, if your interfacial tension between the feed and the extraction solvent is lesser than 5, this will result to a system that will emulsify. So when we speak of emulsification, your feed and your solvent will have a tendency to produce what we call a colloidal mixture. If it's a colloidal mixture, there's a great difficulty of having the dispersed particles settle down, or actually they are indefinitely scattered all throughout your solution because of what we call as the Tyndall effect. So we don't want an interfacial tension that is lower than 5. For systems with higher value, meaning beyond 25, dispersed droplets tend to coalesce. They're trying to group themselves together or form one big droplet, resulting in low interfacial area. We want these droplets to be, shall we say, separated from each other so as to increase interfacial area. So if they tend to group themselves and form one big lump, then we decrease the interfacial area. If we decrease the interfacial area, then mass transfer is also decreased. So we don't want that to happen. There will be poor mass transfer performance unless, of course, if this phenomena cannot really be avoided unless we make sure that there's some form of agitation in our extraction equipment. That way, our droplets will not form one big lump, but they'll be infinitely separated from the other droplets to increase interfacial area. Okay, industrial hygiene has something to do with being toxic, with our solvent being toxic. So it would, since it's being handled by operators, it's being handled during the process of, shall I say, warehousing and even use in the process. So it's important that it will have low mammalian toxicity. And in the case of those processes that is happen, that's being carried out in western part of the globe where there's snow, where they need to have increase the temperature of the, let's say, the storing area. That way your solvent will not, shall we say, will not freeze, will not freeze. So it should have a good warning properties as desired. Something to do here on the freezing point. So low toxicity and low thermal absorption rate reduce the potential for injury through acute exposure. So we don't have this. Has to be safe. Solvents that are liquids at all anticipated ambient temperatures are desirable since they avoid the need for freeze protection or thawing, as I've mentioned in the case of those processes that are being performed on countries or regions where there is snow. Okay, for economic reasons, we want our solvent to be used not only in extraction, meaning it could be really like its full capacity would really be exhausted. So it could be have multiple use. So it is desirable to use the extraction solvent as a material that can serve a number of purpose, not just the solvent for your particular extraction process. Now, in terms of sustainability, then environmental requirements should be adhered to or should be complied with. So solvent must have physical or chemical properties that allow effective control of emissions from vents and other discharge streams. So meaning they could be easily controlled if they are accidentally disposed to bodies of water that may harm living organisms, even the aquatic environment. So preferred properties include low aquatic toxicity and low potential for fugitive emissions from leaks or spills. When we speak of a fugitive, it has something to do with a person that or somebody who has done something wrong and it's difficult to really like catch up with. So it's the same thing with these emissions of unwanted emissions or leaks or spills of our solvent. Meaning, if we use a solvent, it could be easily containable if it's accidentally spilled out on an environment where it should not be spilled out. It is also desirable for a solvent to have low photoreactivity. So it should not be photoreactive in the atmosphere and be biodegradable so it does not persist in the environment. Okay, for sustainability. So these are the things that are written to in solvent properties. I thought I'm done, but we still, I think, have these two as the last. So materials of construction. It is desirable for a solvent to allow the use of common, relatively inexpensive materials of construction for your equipment. Okay. Uh, we may have a very, shall I say, cheap solvent, but the equipment will be utilizing very expensive materials because probably it's corrosive or you need to have a material that will be highly compatible with your solvent. So then that will translate to extra cost. So we don't want that to happen. The solvent has to be available and not so costly. So solvent should be readily available at reasonable cost. So considerations include the initial field cost of your equipment, the investment costs associated with maintaining a solvent inventory in the plant in the case of solvents that are to be imported. So the processing industry must have a certain shall I say, reasonable inventory. So if you have to keep a certain material in your inventory for a desired period of time, that means money being stored just waiting to be used. So dapat hindi amo na. Okay? Um, okay. So I think I'm done with this, hopefully. Now, when we speak of problems here, associated with extraction, it has something to do with having to consider equilibrium relationships or equilibrium conditions. And when we speak of concentrations, whatever process we're talking about, the mole fraction or the weight fraction of your components in a mixture should have always a sum equal to 1. So in this case, I have only indicated as a sample the concentration in the raffinate or the feed, because it's represented as X. So if you have three components in your feed, if you have three components in your raffinate, the sum of their mole fraction should be equal to 1. Okay. Um, in terms of variables to be considered during the extraction process, the operating temperature and pressure most of the time is specified. And we don't have any problem with it because most of the time it's just the ambient temperature. And of course, the very important concentrations. Now, what makes extraction unique, actually, each of the separation processes that we're going to discuss have their own degree of uniqueness from the others that that will help you readily recall each of the separation processes. Now, in the case of liquid-liquid extraction, if in distillation you have curves, you have operating lines, but your X and Y axes are the same, and you have a simple box where these curves are placed into. In the case of liquid extraction, you have what we call triangular diagrams. The one that you see is obsolete already. Yeah, it's not being used, but who knows? They might just be asking you to read concentration of a particular mixture in extraction from the what we call triangular diagram, or this is an equilibrium data using a triangular diagram. What you have in this diagram here, if you move from left to right, so you have here component A. In extraction class, most of the time A is solute. Okay, it's the solute. Now, in here, on the next tip here is B. So from A, which is 0, to 1.0. So A at this point here is 0. 0.2, zero point 0.4, zero point 6, zero point 8, and 1. So we read out here parallel to the side of the triangle for A. Now from here, we have B. So from this side, 0 to 1.0, that's your B. How is the reading of the B? It's parallel to this side of the triangle. So this is 0.2, zero point 0.4, zero point 6, zero point 8, and 1.0. So from 0B to 1.0. And extraction, what is B? B most of the time is water. Okay, water. A is solute, B is water. And I think you know now what C is. So C is 0 from the apex of this triangle to 1.0 on this side here, which where your A is starting. And you read out the calibrations here parallel to this side of your triangle. So we always read the values of A, B, and C parallel to the side of the triangle. 0.2, 0.4, 0.6, 0.8, and 1.0. If A is the solute, B is water, C is your solvent, or specifically your C is your extractant, the one that selectively takes out A from your feed mixture. So if this M here, if this is M, uh, and you're asked to determine the composition of point M on this particular equilibrium triangular diagram, then A is, so we'll say B is 0.2, I stand corrected. B is 0.2, C is zero point 0.4, and A is zero point 0.4. So we start with A here, class. I stand corrected. So 0 to 1.0, that's for your A. Then this is for your B, and this is for your C. Okay, so 0 to 1.0 because we have here 0.4 for A. And for B, we have 0.2 from left to right. And for C, we have here going up. So this is 0.4. So then our mixture M must have this composition for A, B, and C. If you know already A and B, then you can just subtract from 1 the sum of those mole fraction and you will have the C. So any two known, the third one will be known as well, because you only need to go back to the equation here in terms of the sum of the mole fractions of each of your components in the mixture. So this could be given, and you will just be simply asked on how to determine the concentration of a point on that diagram. Or it could be something like this. You can read this in John Couples. I took this from John Couples, but in your handbook, you have an equivalent here. So everything here, by the way, or everything that you see in my slides, figures and sections are taken in your handbook or in reference to your handbook. Now, this is a triangular diagram with partially miscible components. What does this mean, or how does John Couples or your handbook explains this? This means, class, that your solute A is both soluble to B and C, both soluble to water and your solvent. However, B and C, water and your solvent, are partially miscible. They are partially miscible. That explains that you have now in your mixture what we call a one-phase region and a two-phase region. So in here, you have one-phase region, and in here, you have a two-phase region. This P here is what we call as the plate point, and it says it refers to a condition wherein, let's say, for example, we have a mixture M, and we had it separated to these two phases A and B. So they are connected by what we call an equilibrium tie line, because these two phases A and B are said to be at equilibrium. So at the plate point, class, these A and B are identical. So they meet here at the plate point. Okay? So M is the original mixture, and this mixture, when separated, will produce these product phases A and B, which are said to be equilibrated. Just like the first one, this is also obsolete. I'm just explaining it just in case you will be asked to explain what this particular figure means. Excuse me. John Couples has a short explanation of this, but I think it's complete in terms of the what he's trying to explain. Now, the most common type of equilibrium diagram for liquid-liquid extraction comes in this form. It's a pair of two diagrams. One you have a rectangle, the other one you have a triangle. Most modern books and problems and extraction are using this particular diagram already, so they come in pair. So let me go back. Excuse class, I need to drink water. The diagram that you're seeing here, this one, actually came from this. So this is a sample liquid-liquid equilibrium data for acetone. Acetone is your solute, water is B, and methyl isobutyl ketone as your solvent. So for your system at room temperature, so 25 to 26 degrees Celsius. Now, the last two columns that you have here gives you the acetone distribution in weight percent. So another difference of extraction from the previous two separation processes is we're so used to having mole fractions. In the case of extraction class, we use weight percent or mass percentages. Okay, so you have here in the last two columns the water phase and the, shall I say, this is your raffinate water phase, and this is your extract phase because this is your solvent rich phase. MIK is your solvent. Water is water. So this is your raffinate, the water rich phase, and this is your extract, your solvent rich phase. Now, how is this two pair or two columns used in the construction of this particular diagram? So this is it. I think you could see here, you have water phase and MIK phase. In here, you have the water layer and you have the ether layer. So the horizontal axis is the composition of acetone in the water layer. The y-axis is the composition of acetone. This one is for ether, by the way. I'm just using this as an example. And this one is for your MIK layer. Okay, in this case, your, shall I say, this one is for the ether. as the solvent. In this particular table, your solvent is methyl isobutyl ketone. But nonetheless, if you have this data, you can construct this particular diagram for this particular system. So the problem may give you this or may give you this one to use in solving for whatever it requires you to solve. The 45-degree line, of course, you are to draw. You are to draw because it's simple to draw. It's just a line in which the slope is equal to 1. Now, this curve is already the processed or the processed curve after you have plotted this set of points. You plot this, you will have this curve. Okay? That's your equilibrium line. It helps you establish what we call as the tie line here, the equilibrium tie line here for your upper triangular equilibrium uh, diagram. Okay, in this part here, you have three columns, the MIK, the acetone, and the water. The data that you'll be using is only for the first two. You need only the acetone weight percent and the MIK weight percent. Or you only need the solute weight percent and the solvent weight percent. And if you go back to this particular diagram, this is your solute and this is your solvent. So these two columns, when plotted, will give you this curve, this one, the curve that you are seeing here. That's the curve that you will be producing after you have plotted the two columns, except the water column. So if you solve problems related to extraction, which is relying on the use of this equilibrium diagram, on the upper part of this, what we call the phase envelope, this curve, the upper part, so the upper part is in here, you will have the extract. You will have the points corresponding to the extract. It will give you the composition of the solute and the solvent in the extract. If you have here the upper part of the phase envelope. Below, you have the raffinate. So the lower part of this phase envelope is the raffinate layer. Again, if you have a point in here that will help you find the XA, the solute present in the raffinate, and the solvent present in the raffinate. So for I. So I is raffinate and G is extract. Now, you may wonder how was this equilibrium tie line established? This one, the equilibrium tie line. If you have an original mixture that will be represented by this point H, so meaning the composition of your mixture, if I'm going to read from here is 1, 2, 3, 4, 5, is zero point 0.1 solute and 1, 2, 3, 0.3 solvent. So meaning the rest is water, which is zero point 0.6 because this is zero point 0.1 and this is zero point 0.3, so that's only zero point 0.4. The rest will be water. So this is your original mixture. If you will have this original mixture settled and the two phases separated after you have processed after the extraction process, this I and this G will be only determined through the process of trial and error in this particular diagram. What we do, let's say for example class, I will annotate example lang. I will have, I think example, this is where my G is. Okay, that's my G. So what will I do to be able to find the I? I'll go down from the G that I have selected. I'll end here on the 45-degree line. Then I'll turn right. I'll end here on the curve. Then I'll go up until I reach the raffinate. Now, I will say that this is the corresponding extract and this is the corresponding raffinate phases produced out of equilibrating my H. If I will connect these two, let's say for example, I will connect this point here and this point here. It should pass point H. It should pass point H. If it passes point H, then the equilibrated phases after extraction has proceeded for this mixture, for this feed mixture of mine, will be this extract phase and this raffinate phase. So the composition I can readily read here. I read the solute here, I read the solvent here. The same thing for the raffinate. This is the solute and this is the solvent. In this case, of course, this is not it because wala man naagyan si H. So dapat maagyan si H. So I'd like to clear it, to clear what I have done. So in this case, you have here G, for example. This is your guess. Okay, napata sa aga nag-guess. So this is your guess where your extract is. You go down until you reach the 45-degree line. You turn right until you reach the curve. You go up until you reach the lower part of the phase envelope. When you connect G and I, your guessed extract and raffinate phases, if it passes to H, then these are really the product phases, the equilibrated product phases out of processing this feed having this particular composition. So it's a tiring thing, but it will not consume more than 5 minutes of your time. What I mean is, will not consume how to find, will not consume much time having to find, excuse me, the extract here and the raffinate, wherein you need to pass through the given composition of your feed. Hindi mo man siya pagtaman kapalagpat nga diri ka kabalo ka gid hindi mo maagyan si H. So you have to select a point here or a point here. You may start on the raffinate. You go down until the curve, you turn left, and then until the line, then you go up. And then you try to connect the two points that you have on the upper and the lower part of your phase envelope. If it will pass through your feed composition, then good. This is already your equilibrated product phases. And it will give you right away the composition of the extract and the raffinate layer, which you will of course need in subsequent material balance requirements that your problem may ask from you. Okay? Any questions so far as to the process of determining this one? Is it clear to everybody how we establish the tie line? So no question? Okay, so I'll go back. So I'm on my slide. So this is your equilibrium diagram based on this table. So if you're not provided with this, the problem should provide you with this. If this is not provided, the table should be provided for you. Okay, so we have this particular sample problem, a simple sample problem taken from a John Couplis. And I will end with this because it's, I think, 8 minutes for time. So I can write here to save us some time. So you're given an original mixture weighing 200 kilograms containing 50 kilograms of isopropyl ether, 20 kilograms of acetic acid, and 130 kilograms water, which is equilibrated in a mixer settler and the phase is separated. So determine the composition of the raffinate and the extract layer. So the only thing that you will need here, class, is a very simple manner of determining the composition of your feed. So if you have a feed which is 200 kilograms, so if you need the composition of acetic acid, because that's your solute, then that would mean 20 divided by 200. So this is your 0.10. Then you need the composition of your solvent. So XC, you need C. By the way, these are small x class when you write it. So XC is your isopropyl ether, which is 50. We divide it, of course, still by 200. So we have here 0.25. Now, what will you do with this? In your triangular diagram 4, so your system should be acetic acid, water, isopropyl ether. That's your system. You look for, let's say, for example, I'll go back to this triangle that we have here. I have here a 0.1 and a 0.25. So for A, which is 0.1, you look for a 0.1 here. This is 0.1 already for A and a 0.25 for C. Let me erase what I have here. So a 0.1, this is a 0.1, this is 0.1, 0.2, 0.25. So this is my point here. And all you have to do is find the extract and the raffinate based on the procedure that I have discussed with you. The corresponding relocation of the extract here, let's say for example here, and the raffinate here, if you connect, it should pass to this point, which is representing your feed. Then this is already the thing that is being asked by the problem. Because the problem is asking you to determine the composition of the raffinate and extract layers only. So that's it. Actually, the procedure that I have discussed to you a while ago is the same procedure that you will use in this particular sample problem. So the only thing that you did is determine the XA and the XC in the feed. That way, you can have your feed plotted here in your diagram. So by the way, the diagram that you are to use is of course the diagram for ether, acetic acid, and water. And I think this is the one that we're looking for. So this is ether, and this is acetic acid. If you have a different system, which I'll be giving you also so that you will know how to construct this on your own, then you have to construct this and have your own phase envelope, and you should have your own equilibrium curve here at the bottom. That way you can determine what the problem is requiring from you. Unless it's a problem which is purely a design problem, which does not rely on this graphical approach. You don't need this. You simply need graphs for that matter. Okay, I will stop sharing now and I will pause the recording here. I'll stop recording.